Okay, the next thing that we'll do is we'll find a polynomial of degree 3 whose zeros are -1, 1, and 3. Okay, so the first thing that I do is x minus r is a factor. So x plus 1 times x minus 1 times x minus 3 would be the three factors. X plus 1 times x minus 1 is x squared minus 1 times x minus 3. When I FOIL that out, I get x cubed minus 3x squared minus x plus 3. Okay, and that'd be one answer that I could give. Now another answer that you could give, another polynomial, could be where you have the three factors, just as we had before, but suppose you have a number in front. Not 0, but any other number. Okay, well I would just multiply the number by these four terms. 5 times 4x minus 15x minus 5x plus 15. In fact, any polynomial of the form where you have the three factors times a number where the number is not 0 is going to work out. Suppose that f of 2 is equal to 6. Okay, f of 2 gives me, f of 2 means that x is 2, and so I want to replace x with 2. A times 3 times 1 times -1 gives me -3a. -3a gives me 6. Okay, so a is -2. And in this case, there would only be one answer. Okay, if they told me a point was on the graph, such as f of 2 equals 6, 2 6s on the graph. If a factor occurs more than once, then the 0 is referred to as a 0 of multiplicity. So here's an expression. Suppose that f of x is equal to 3 times x minus 4 times x plus 1 squared times x minus 2 to the 4th. Let's identify the zeros. So r is a 0. Okay, notice that 3 has nothing to do with r. Okay, x minus r. 4 is a 0 with multiplicity 1. -1 is a 0 with multiplicity 2. And 2 is a 0 with multiplicity 4. All I'm doing is I'm looking at the power of x that I see. Again, 3 has nothing to do with any of this. Okay, 3 has nothing to do with any of this. As a note, this would be a degree 7 polynomial, and so it would have 7 zeros, not 3. Not 3. Some of the zeros repeat, which is common and typical, but when you add up these numbers here, you get 7 total. Okay. Let's find all the real zeros. F of x equals 3 times x minus 1 squared times x times 2x plus 5. Okay, well 3 is 1 is a 0 that has multiplicity 2 because its factor is seen twice. So all in all, I've got 3 zeros, not 2. Okay, I've got 3 zeros. Okay. Another expression, f of x equals -2 times x plus 1 squared times x squared plus 4 cubed. Well, I divide by -2, and x equals -1/3. X squared equals -4 means that x would be plus or minus the square root of -2, which would have complex zeros. And the directions here, I want to find all the real zeros. Okay, so this would only have one real or 2 real zeros, since it has a multiplicity of 2. there are 5 zeros total. Okay. F of x equals 4x times x squared minus 3 times x plus root 5. Okay, so I got this set equal to 0, and 4x equals 0 means that x is 0. X squared minus 3 equals 0 means that x is equal to plus or minus root 3, and x is equal to negative 5. All 4 zeros have multiplicity 1. Okay, so that would be important there. The next thing is even and odd multiplicity. Let x minus r to the n be a factor of a polynomial f of x. If n is odd, then the graph of f crosses the x-axis at the point r0, and if n is even, then the graph of f touches the x-axis at the point r0. So here's an example. This is a polynomial, by the way. Of course, it's been factored for me, but if I were to expand this out, I would have something that has 5 terms to it, and this graph touches the x-axis at negative 4, 0, because the power is 2, and it crosses the x-axis at 3, 0. Okay, since I've got an odd degree power. The turning points, if f is a polynomial function of degree n, then f has at most n minus 1 turning points. Okay, and a turning point is where we go from increasing to decreasing or decreasing to increasing. For example, suppose that f of x is equal to 6x to the 4th minus 3x cubed plus 2x plus 2x plus minus 5. First of all, this would be a polynomial, a degree 4 polynomial. Okay, since 4 is the largest power of x that I see. And this would have at most 3 turning points. Okay. Could have 2, could have 1. It probably doesn't have 0, otherwise it'd be a line. But at most 3 turning points. Okay, the end behavior for large values of x, positive or negative, the graph of a polynomial resembles the graph of y equals a sub n times x to the n power. Okay, so the input here, n greater than or equal to 2 is even, and a sub n is greater than 0. Well, a sub n is the number in front of x to the n, and now we don't know what happens here. Okay, it's going to be different for x squared, for x to the 4th, for x to the 6th, or whatever. But we know that on both ends the parabolas, the graph is going to open up. Okay, if n is greater than or equal to 2, and that's an even number, and a sub n is negative, I think transformations, think rotation about x, so I would have something that'd be facing downward here in both directions. Again, I don't know what this middle part looks like, but I know what happens on both ends. If a sub n is, or if n is greater than or equal to 3, and that's an odd number, and a sub n is positive, then the graph is going to resemble y equal x cubed. Okay, where you're going to be heading down in quadrant 3 and up in quadrant 1. And if n is greater than or equal to 3, and that's odd, and a sub n is negative, then you're going to be in quadrant 2 and in quadrant 4. Okay, think a reflection about x, okay, to get this graph right here. So, for example, on page 197, problem 62, f of x equals x minus 1/3 squared times x minus 1 cubed. Okay, so what are we supposed to do here? We're supposed to, here's the function. Now I'm supposed to, part A, list each real zero and its multiplicity for each polynomial function, so that is a polynomial. Part A, list each real zero and its multiplicity. Part B, determine whether the graph crosses or touches the x-axis at each x-intercept. Part C, determine the maximum number of turning points on the graph. And Part D, determine the end behavior. That is, find a power function on the graph of f that resembles large values of the absolute value of x. Okay. Let's see here. So, part A, I need to list each real zero and its multiplicity. 1/3 and 1 are the real zeros. 1/3 has a multiplicity of 2. 1 has a multiplicity of 3. Okay. Part B, determine whether the graph crosses or touches the x-axis at each x-intercept. Okay, well, at 1/3, we've got a multiplicity of 2, so I know that the graph is going to touch the x-axis there at x equals 1/3. Think of like y equals x squared, you know, something simple, you know, where it touches at y at x equals 0. It's going to touch at x equal 1/3 and cross at x equal 1, since there's a multiplicity of 3. Part C, determine the maximum number of turning points on the graph. Well, if I were to FOIL this out, the leading factor that I would have is x to the 5th. Okay, if f is a polynomial function of degree 5, let's say, then f is going to have at most 4 turning points. Okay, so there's going to be at most 4 turning points. Part D, determine the end behavior of the function. I've got a degree 5 polynomial, and a sub n would be positive. A sub n is 1. So the graph is going to resemble what I see here, where it's going to fall down on the left and open up on the right, resembling y equal x to the 5th. Okay, since they have a degree 5 polynomial there. Problem 74 is f of x equals, and let's see, problem 74. Construct a polynomial function that might have the given graph. More than one answer is possible. Okay, so problem 74, it looks like I cross at 0, I touch at 1, and I cross at 2. Okay, and there's 3 turns that I can see. Okay. Oops. 1 turn, 2 turns, 3 turns. Okay. So, in order to construct this polynomial, I would have, since we cross the x-axis at x equals 0 and x equals 2, then x times x minus 2 are going to be factors. And since we touch the x-axis at 1, then at 1, 0, you're going to have something that has an even degree. By the way, the reason why I noticed that there's only 3 turns on the graph showing would indicate that I must have a degree 4 polynomial. I must have that. In other words, I would not want x times x minus 1 times x minus 2. Okay, because that would only be a degree 3 polynomial, and I need that degree be a degree 4 polynomial. Okay, why don't we stop right there? We still have a couple more problems left in the section here.